Alright, welcome to 1415-2, which is entitled The Physics of Music, uh, the Physics of Sound. What I've got, every single musical instrument, it doesn't matter what type of musical instrument it is, every musical instrument you can think of makes its music from something vibrating. Meaning a brass instrument, a woodwind, a string, a percussion, anything. Something is vibrating. Now what that something is, it depends. So for a percussion, the surfaces vibrate. The cymbals, the drum heads, they're vibrating up and down. In a brass instrument, it's your lips that are vibrating. In woodwind instruments, it's the reed that vibrates, and that's a sub-contra bass saxophone. For those that are interested, I'll include a link to one being played. In stringed instruments, the string vibrates. Now, there's one that I didn't quite get to, like something like a flute. In a flute, there's no surface, your lips don't vibrate, there's no reed, nor are there strings. What's vibrating inside of a piped instrument? And it's a column of air. And that's where I'm going to focus a lot of our talk today, on a column of air. So the first place I want to go is to a website which kind of demonstrates what's going on inside of that tube. Here I've got a tube, and this tube is right here. Now we call this a closed tube because this end is closed and this end is open. So this is what's called a closed tube resonator. Now what's going on inside of here is resonance. At the closed end, you'll notice that if you focus on the particles, they're not moving. Those are called nodes. And if you look at the particles down towards the open end, they're moving quite a bit. That's an antinode. You'll notice right below it, right here, this is a longitudinal a transverse representation of what's actually happening, but it's longitudinal. So what's important to know, that when you have a closed end, you have a node. And when you have an open end, you have an antinode. That's an essential understanding right there. Knowing that you have a node at the closed end and an antinode at the open end. And this is what happens. And this right here, this much of a wavelength, if you look, this is 1/4 of a wavelength. Because you go down, that's a half, that's 3/4, and that's 4/4. So what we've got right here is 1/4 of a wavelength. Now I can go to a higher pitch right here. You'll notice I still have a node on the closed end, and I still have an antinode over here. But now, this is not 1/4 of a wavelength. This is 3/4 of a wavelength. Count with me. 1/4, 2/4, 3/4, 4/4. So this length right here would be 3/4 of a wavelength. See if you can see a pattern. If you'll remember, our first one was 1/4 of a wavelength. Let's go to our next. Again, we have a node at the closed end and an antinode at the open end, but this is 5/4 of a wavelength. So 1/4. Let me undo this. 1/4, 2, 3, 4, 5. So my first one was 1/4 of a wavelength. My second one is 3/4 of a wavelength. This one is 5/4 of a wavelength, you can start to see the pattern. 1, 3, 5. This next one's going to be 7/4 of a wavelength. This is what's resonating inside of flutes, inside of bagpipes, inside of, like, if you blow over the top of a bottle, like that classic blowing on a jug. Now, let's go to having one side open. Step back down. And you'll notice one other thing I want to point out. This is called the fundamental. When you're at your lowest note that you can play, that's the fundamental. When you go one higher, we call it the first overtone. One more, second overtone. Now let's open up both sides. Both sides open. The difference here, here's the big difference. You've got an antinode on both ends. An antinode on both ends. How much of a wavelength is this? This is 2/4 of a wavelength. So 1, 2, 3, 4, and that would give us one full wavelength. So the first one, 2/4 of a wavelength. Look at here. Here's the next one. We've got antinodes on both ends again. This one is 4/4. 1, 2, 3, 4. Here we've got 6/4. Now you start to see a pattern. 1, 2, 3, 4, 5, 6. So the first one was 2/4. Second one is 4/4. Third one was 6/4. And the next one's going to be 8/4. Each time they're stepping up by half a wavelength. That's exactly what was going on with our closed tube. But these are even, 2, 4, 6, and 8. And if you remember back to our closed ones, they were 1, 3, 5, and 7. Important similarities, they step up by half a wavelength. Important differences. The open tube starts at even, so 2, 4, 6, 8. The closed tube starts at odds, 1, 3, 5, and 7. So in your book, they have these illustrations, and these illustrations were meant. This is what that animation I was just showing you is referencing. So this is an open tube right here. Open tube, our first one is half a wavelength. Here, or you might want to say it in these terms. Here you've got a full wavelength. Here you've got wavelength. Each time it's stepping up by a half wavelength. With a closed tube, we've got nodes here and antinodes. So this is 1/4. This is 3/4. This is 5/4. Again, they're both stepping up in both cases by half of a wavelength. Classic example problem here. It says there's a tuning fork that has this frequency. It's used in a closed pipe. The loudest sound is heard when the column is 21 and the next one is 65.3. So you've got a tube that's closed and you've got some wave. Remember, you have to have a node here and an antinode. So I'll just draw a random wave, and let's just pretend that this distance right here is 21 centimeters. And then if you made the tube a little bit longer, let's say 65.3, you can also get it to resonate. Now remember, this is half a wavelength. So half a wavelength is equal to the difference of these. So this distance right here is, let's see here, subtract those, you get 44.3. So the full, so one wavelength, you double that and you get 88.6 centimeters, or 0.886 meters. The question wants to know, what is the speed of sound? Velocity is equal to wavelength times frequency. Oh, how nice was it that I just found that I can find the wavelength to be 0.886, and the frequency I'm playing is 392. So the speed of sound in air, you multiply these two numbers, and you get 347. And you ask yourself, does that make sense? Sure does, because the accepted value is 343 meters per second, but that's when it's 20 degrees outside and depending upon the atmospheric pressure, 1 atmosphere. So it might be either a little bit hotter or it's under a little bit more atmospheric pressure. And that's how I can utilize resonance in cavities. The last couple things I want to touch on before I go is tone color. How can you tell my voice from anybody else's voice? How do you know a tuning fork, a flute, and a clarinet? How can you tell the differences between those things? If you look at these, each one of these things is playing the same note, meaning that the distance from peak to peak is the same in all of them, and they're playing at the same volume, because notice the wave heights, they're all the same height. So if they're playing the same note and they're playing the same volume, shouldn't it sound the same? And the answer is no, because it depends on the tone color. Now, if you look at the physical shapes of the waves, a tuning fork is a very pure tone. The fork itself goes in and out very nicely. But when you have a flute, you've got an overtone. So it's actually this is literally a wave within a wave. So it's tough for me to draw, but you'll see that there's peaks right here and right here, and notice how these are equally spaced. Here's one wave. One of these waves literally looks like this. So let's see here. So there's a wave inside of this wave. Same with the flute. There are what are called overtones. It's got a physical there's a difference in the vibration from the clarinet to the flute, which gives it its tone color, or timbre is what it's called. When you play chords, if you play them together and they sound good, we call that consonance. And when things sound bad, two notes when you sound, you're like, oh, that's awful. That's called dissonance. And lastly, the beat. There's such a phenomenon called the beat frequency. The beat frequency is when you play two notes that are really close together. Two notes that are really close together, but they go through alternating constructive and destructive interference. So if you look right here, I've got a couple of waves, a wave at the top and a wave at the bottom, and they're being alternating, adding and subtracting. So I've got this one right here. Take a look at this special point right here. They're both at bottoms, so they add together to make a really big noise. But look right over here. This one's at the top, this one's at the bottom. They cancel each other out, so you get a faint voice. So if you're playing something like 392 hertz and maybe 390 hertz, what you're going to be hearing is a beat frequency, a wow, 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 alternating loud and soft. And to figure out the beat frequency, you just subtract the two frequencies. So 392 minus 390, the beat frequency in this case is going to be 2 hertz. This is what your band director is listening to when they tune you. They're listening for that beat frequency to see when you're in tune.